Hey everybody, this is Larry. This is me going over Q4 of the weekly contest 288, maximum total beauty of the gardens. So this one is a very hard problem. Don't feel bad if you don't get it. I'm not confident, when I solved it, I wasn't confident when I submitted it, which is how I got two wrong answers, which you can kind of see in the video later, but also just in general, I'll go over it. But the idea is, in a way, so there are two. What makes this problem hard is that there's a lot of math, and also is kind of two or three ideas put together, and you really have to kind of put them together to get this one. So in one way, I'll explain it in a couple of things. The first thing is brute force. So the way that I did it is, and you can kind of watch me solve it live, but I thought about a lot of different ways to be just like different permutations of how I can attack this problem. And the way that I kind of think is, okay, if I could brute force something, can I do something cheaper to the other thing, right? And of course, given that n is 10 to the 5th, if you use two brute force, or something that's two brute force, it'll be n squared. And n squared obviously is going to be too slow, so that's no Gucci, right? But then I think that idea was something that I explored during the contest, and I'm explaining this because I want to not just explain the solution, but my thought process, and maybe that'll help someone, because I think that's more interesting than just the solution, where you think you get it, but maybe not. I don't know. But yeah, so then my idea is, okay, let's say we have. So that was my idea, is that we brute force, we have one full flower, two full flower, three full flower, four full flower. Can I figure out how many partial things on it? Or I even thought about the other way. Let's say we have one flower part that's partial. Can I make the rest full? And then I thought about various ways of binary search just in general. I even thought about ternary search. Maybe like if I use X flowers on getting them to be full, and then the rest on the partial, does that make sense? I couldn't really prove it to myself. Maybe it does, maybe it doesn't. But in the end, I did something that I absorbed a property that I wasn't sure that I was able to prove, to be honest. But that's basically the idea. And the idea is that let's say we could brute force the number of full things, and then figure out what is the flower level. I call it water level because I think about it as a water, and I'll draw some diagrams to show why does this later. And then I can brute force. Okay, let's say we make the first or like the and the thing that you want to do, of course, is do greedy on making full gardens, right? I think this part is. I think this part is self-explanatory. Obviously, to save flowers, you want to grow flowers at the most, like the one that's most full. You don't have to use as many flowers, so then you could save them to build more flower gardens later, right? Something like that. That's the idea. So then, basically, the idea I had was. Do I have a? Okay. So let's say I had this one. So first I saw it, and this obviously. This is fundamental, so it's fine. But basically, for example, I had, I'm going to do some drawing later, but just to kind of, so let's say I had this example and I sorted. I'm just going to add a couple more for funsies, and maybe one dupe just for fun. And let's say target is still equals to 5, right? So then the idea is okay, let's say, what if one flower garden is full, right? Then I go, okay, then the rest we do the math on, let's say we have new flowers is equal to, I don't know, 20. Let's say one garden is full, then we go, okay, what is the flower level of the minimum after that, right? So that's basically the idea. And then now we brute force test, okay, let's say two garden is full, and then, let's make this a little bit higher because actually that makes more sense. But let's say now we do here, then we go, okay, let's say we made these 5 flowers full. That means that I have to put 2 flower here, 1 flower here. So that means that I have 17 flowers left to put on the left. And then what would be the flower level of that one, right? So so let's say you have a magical function to tell you that, then this would be or if you have a magical function that tells you that in less than linear time, then that'll be fast enough. Because now what we want to do in my head is that now we have going from right to left, we have O of n iterations, and then now we have each iteration will take some, O of f of n time. And in my head, of course, if f of n is equal to is O of n, then that means that running time will be n squared. So instead, which in my head I go, okay, is there an O of 1 or O of log n algorithm to figure this out? So that's basically the idea. And the way that I did it is kind of tricky. I don't know if I think possibly, to be honest, there's a easier algorithm or easier math. But as you always, as I always say to people at home, I am really bad at math. So sometimes I prove a lot of things that a lot of people take for granted. So yikes, right? But and I'm kind of stalling a little bit because I'm trying to pull out my drawing pad. But yeah, so basically the idea that I have here to get this running time to be fast enough, as we kind of showed, is by doing binary search. So then the idea that I had was something like this, where, okay, let's say I have, this, okay, so let's say, this is all sorted, of course, crooked line, ignoring the crooked line, and I drew too many. And let's say that they're sorted. I'm bad at drawing, so yeah. And then the idea is that, okay. So the idea I had is that if, and this is like an area type thing, right? Of, okay, let's say, this is a sub 1, a sub 2, a sub 3, a sub 4, ... right? Let's make it this way. So no, that's okay. Okay, fine. Let's make this a full thing so I could demonstrate this a little bit easier. Right? So you have something like that, right? I think this is a better visualization, I think. So this is A1, A2, and pretend that my drawing is bad. Pretend that these are perfectly, like increasing, right? Okay, so pretending that they're increasing, then the question is, okay, let's say I have some leftovers, right? Let's say, the way minimum work is that if we look at something like this, let's say we add enough, and everything in the blue or cyan or whatever is the leftovers, right? So everything here is the leftovers, right? So that means that, for example, oops. Oh, snap. Let's say that, this height is part of the leftover, this height is part of the leftover, this height is part of the leftover, and all these red squiggly lines add up to the new flowers that we're planning, so that we go to that height. And so then now we go to that height if we have a rectangle of area equals to height times the number of flowers, right, that are within to the left. So that's basically the idea, is that, okay, given this, how do we figure this out, right? Well, so there are a couple of scenarios. Let me take this back for a little bit. So there are a couple of scenarios, right, in trying to figure out how many flower beds to fill up, and how to binary search. So then the idea is that you only have a few cases. One is that, let me change color, that's why I'm taking so long. One is that, let's say you have something like this, right? Something like that, right? Say, let's say you draw your thing such that, you know, it's something. So let's say you drew it such that it is, you know, let's say you only care, let's say these two, it's already full, right? If it's this, then that means that you have too much flower. And then the other case is similar but opposite, which is that, oh yeah, actually I think I explained this one a little bit wrong. Let's say that we want to fill all 5 of them, but we want to see whether this height is good enough. Well, this height will only give you 3 fills, so that's not good. So that's basically the idea, is that you binary search to see where, okay, this means that we need to, you know, even it out, if you will, so that we want to binary search so that it's here. And in the other case is that you're too low. If at this point where the height of the thing is smaller than the height of the next thing, then you know that you have enough because it fills everything completely, right? That means that you don't have any more leftovers. Otherwise, if you have leftovers, then that's not good. That's basically the idea. I think I'm drawing it really weird, to be honest, and I apologize. But we'll go over it in code, and hopefully in code that's better. But that's basically the visualization of using the area and doing that. And now that we talk about the area of this rectangle, the orange one that we have on top, let's say we have this area thing that we talked about, right? Well, then you should see that here, this area is now, you can find the sum of these areas by prefix sum. So that's basically the idea that I did. Yeah, so now I'm going to just remove this now. Hang on. And yeah, so that's basically the idea. Well, let's go over the non-binary search code first. But basically, yeah, this is the non-binary search code. This is me saying, okay, no full flowers. So this is the cost of what happens if there's no full flowers. We do the binary search to see what the height of that is, and then we times the partial cost. Otherwise, we do a brute force going from right to left on going, okay, this one's full. What is the cost? What is the partial, like what is the min of the partial min on the left side? And that's basically the thing that I have. I remove the flowers by making this one full, and if there's no more, or if the negative flowers, we break. Otherwise, we calculate the partial min here, and this is going to be O of log n, as we said. And since this is O of n, this is going to be O of n log n. Yeah. And here, as we said, we calculate the partial min. This is just a count. We calculate the partial min by this binary search function. By saying, okay, this is how many boxes we have at the max. We do binary search to go, okay, this is how many leftovers. What is the first place such that it fills it up without spilling over, right? If it spills over, we have too much left over, then we go to the right. If it has too little, then we go to the left. And that's basically what this idea is for. We have this mid, and then if we fill this up, so we calculate the height of this rectangle. This is that we just visualized. This is the width, this is the area, and this is the height. And if this is the height is greater than the one next to it, that means that we have overflow, so we have to try a bigger number. If otherwise, we try a smaller number because it doesn't overflow, that means that we have used too many flowers to fill, and then that's basically the idea. And then at the end, we return the min of the partial min of this function, and this is the area over the width, which is the height of the rectangle that we talked about. And of course, that can only be max equals to target -1, because otherwise it becomes full. And it's okay to throw away extra leftovers, because the extra leftovers, you can just think, well, I mean, it's okay to throw it away just because they let you, right? So that's basically the idea behind this problem. Yeah. That's pretty much all I have. Like I said, this is O of log n, this is O of n, this is O of log n, and of course we use prefix sum here, which I kind of hand waved over a little bit. Yes, you have to know prefix sum for this one, so I'm not gonna go over that much because this is a very hard problem already. there are other videos on it that I have, so check those out. And there's also one more case where if everything's already full, then you just return full. So I said I had two wrong answers. The reason why I had two wrong answers is because I wasn't careful. Because I wasn't sure about all this stuff that we talked about, so I actually missed two cases. The first case, I missed the no full follower case where you cannot get any full, or you don't want to get anything full. So I missed that case. And then the other one is everything is full. So I missed the only two possible edge cases I missed. And not only that, I had to use two wrong answers for it. So that's a little bit sad, but it is what it is. But yeah, that's pretty much all I have. Of course, this is also sorting, by the way, so it's going to be n log n anyway. But yeah, that's pretty much all I have now. So, oops, one button. Let me know what you think, and you could watch me solve it live during the contest next. But first of all, I'll show you all my code. So you could kind of pause like here and then take a look, and then here's the binary search code. I have some debugging code, and then here's the rest of the brute force things. Let me know what you think, and yeah, ta-da. I don't know if this times out. Hopefully it doesn't. Okay, wasn't sure. Okay, that one was a little bit more respectable timing, but I'll see. And flowers. Okay. What is all this stuff? They don't even tell you anything until the third paragraph. The number of complete gardens. Okay, so find some stuff. You have target is 6, so there's one with 6. And incomplete gardens is 2. Oh, partial is. Wait, why? Oh, 4 gardens. What's an incomplete garden? They don't tell you what. Oh, the minimum number of flowers in incomplete gardens is 2. Okay. I still should define. It's weird. Okay. And then you times it by 1. So you have 6. So one of them has 12. It's such a weird thing, but okay. And then the min is 2, so okay. So n squared could solve it, but that's obviously too slow. Okay. I think you could do ternary search, but I could be wrong on that one. Because you don't always optimize for full. No one solved it yet. Oh, you don't have to use all the flowers even. And in that case, 4 times 6 is 12. So you want at least one partial, maybe. Maybe that's not true. Only in this case. Is this a case analysis problem? Can I do a scan line? I don't even think ternary research makes sense, or at least I can't prove it. Oh, that's way too slow. Surprised no one finished it yet, but okay, let's say we're you don't even have to use all of them. I don't know. I mean, if all the crazy math people haven't done it yet, I don't know if I have any great ideas on this one yet. Because people are very good at math. do prefix sum. Does prefix sum help? I think so, but okay, someone smartphone got it. But I think it's prefix sum, but maybe just do the math on that. Maybe. Can you do a binary search? I don't know if this is true, so we'll see. So much potential for issues. I don't know. I mean, this is probably not right now, but I think the idea is something like this. Twice in a row. New mistake. And 14, that's really not right. You can kind of see how this math goes. To -1. 1 is, what is this? That's not the min, that is that's really not right either, is it? It's giving a 3. Why is it giving a 3? There's 4 left over. I have to do another math on this, and just fine. But there's 2 elements. That's not right. Well, that part is actually right, but oh, this is min, that's why this is weird, but 4. Partial min is 3. That's not true. The partial min should be 2. Why do I return 3? Because this is 2 plus the leftover is 4. So then the 6 over 3 is 2. Right? Is this not 2? No, this is 3. Why? What? This is 6. 6 over 2 is 3. Why is that? The prefix sum is 2. That's true. Plus 4. But this means that. That's weird. Basically, because this is bigger, it keeps getting bigger. Okay, that's good. Then it should be going to the right. Then left should be. What is right bound? Oh, no. So this is scary. Left, right, okay. Right bound is 2. Why is it not? Because it is smaller. And smaller is good, so you move to the left to no. Because this is 3 plus 4 is 7. 7 over 3 is 2. And this is strictly equal to, that's why. It's moving to the right. Maybe this form is a little bit weird. Left over is the tricky part. Basically, it has this shape. As we go to the right, we want to get the first element in which this is less than. Wait, what? So when left is equal to 1, this is 4, this is 3, this is 2, and why is addition this? This is bigger than that, right? What is 7? No, mid is. Wow, I'm just like really bad at math today. Left, right. Okay, so then the prefix is 3, so it's 7. 7 over 3 is 2, right? And 2 is, oh, the next number is actually 3. So this is less than, which is what we expect when it's less than. Then right is a possible answer. Maybe something like that. Okay, so I mean, I fixed this one kind of, but I'm still not convinced this is right. And now a lot more people are gotten it, but I don't know this one still. I thought maybe you could binary search it, but apparently I'm wrong on that one. Okay, so we want 3, 4. So let's see. So okay. So when there's a 3, 3, 4, you have 1, and it goes to 4, which is true, and then this one is 26. Why? Oh no, that's just when there's one number. So okay, so there's 1, 4. That's not even right. The math isn't even. Full count is 3. No, full count is 1. Partial. 4. 4, 6 is 24. And then 1, 4 is 3. Oh, 1, 4 is 2. So that's why it's 26. Okay. 28 is fine. 30 is fine. I think this math is weird. So, okay, so I think this is right, but then now if it's 0. I think that's right. So, left, right is equal to 0, then how does right even get to -1? Oh, because the right bound is I mean, that gives me the correct right answer, but I have doubts. We'll see, because I don't have any other really idea, to be honest. So let's give it a YOLO submit. See what the wrong answer is. Maybe even timeout, to be honest. No, fine. Okay. I don't know how to do this one, to be honest. So I think that's fine. This isn't even close. Actually, this one seems like an edge case, so maybe I'm okay here. Let's see. Oh, I don't do 0 partial, so that's why I missed that one. Or 0, 4. So what I need is, how do I do 0, 4? This is equal to if the sort of the smallest flower is less than less than 4, then best is equal to partial times. No, you still want to fill it up. I think that's why. So okay. So here we have go new flowers. Right. I think maybe that's good enough. Maybe not. N minus 1 maybe. Yeah, N minus 1. 14, still wrong, but I appreciate you for trying. I think it's because I don't handle the last bound really well. Let's see. So the partial is 2 points. We want to basically 4 is 9, so we want 8. Oh no, we want target. So 14 times 2 is 28 is how we get this answer. Why do I have 14? How do I have only 14? Oh, it's because this thing that means that the other stuff would be okay. Also, it's this times partial anyway, so maybe I needed to fix that. Maybe that's just it. Yep. Okay. Wow, that was a silly mistake. Actually, I didn't print anything out. Let's get another wrong answer. Maybe timeout. But this is binary search. Okay, well, that's a little sad. I wish they gave it to us. Just because I don't know. I feel like my idea is kind of alright, but if there's no no, in every other case there should be at least one partial, unless unless we have the case where they're already all full. Yeah, I think I messed that up actually, now that I think about it. There's so many parameters I have to keep track. So this should give me 4 points, I think, unless I'm wrong. Yeah, I think I'm wrong. So because it should have no partial, so okay. So basically, if okay, let's see. I know that this is wrong answer though, so it's fine. If 0 is greater than equal to target, then turn partial full times n. Right. Okay, so that's fixed that one. Let's see again. Get another wrong answer. Maybe still hidden though, so then in that case I don't know what to do. Okay, so that was a silliness because I was thinking about that one a little bit. Hey, thanks for watching. Hit the like button, hit the subscribe button. Join me on Discord, especially if you want to talk about these problems. There are a lot of smart people in the Discord, and you get to even see me. So that's hopefully that's not deterrence. But yeah, stay good, stay healthy, to good mental health. I'll see you later, and to good lead coding. Bye bye.